All right, hello everybody. So this is going to be the very first lecture about Turing machines. The intent of this one is really just to go over the absolute basics of Turing machines and kind of provide an intuitive kind of motivation for the entire thing. So as we usually do, we're going to start off with where have we been? What have we actually been trying to accomplish? And so the first thing we've done is we've covered regular languages and context-free languages and all of the differences between those two things. But we've also really talked a lot about different theoretical constructs that allow us to talk about those languages. So what I mean by this is we've talked about things like DFAs, things like NFAs, things like PDAs, all of the different types of grammars, all the different things like regular expressions that not only represent these different types of language families, but also allow us to answer questions like the membership question that deals with if a string belongs to a specific language or not. So what we're going to do now is we're going to take a lot of that same information that we've been dealing with this entire semester, and we're really going to zoom out to the kind of 10,000 foot view of theoretical computer science, particularly talking about Turing machines, which are really a generalization of pushdown automata, which we kind of discussed maybe about 2 weeks ago if you take spring break into account. So today what we're going to do is we're going to go over the very basics of Turing machines, and then the next lecture is really going to go over kind of the details, the kind of mathematical framework around Turing machines, how to compose them, and that kind of thing. So what we're going to do first is we are going to motivate this entire thing really using intuition rather than math. So if you think back to the pushdown automata lecture and sort of the diagrams that we put together about how those automata worked, we're going to treat Turing machines very, very, very similarly for this first lecture. What we want to do is we want to make sure that everybody's comfortable with the pieces of a Turing machine. We want to make sure that everybody's comfortable with the different things that a Turing machine can actually accomplish. And then we will kind of build the mathematical scaffolding around that rudimentary understanding so that we can kind of bootstrap ourselves to the more complicated stuff that comes next. So kind of labeling different pieces of a Turing machine, we have to start with the control unit. So the control unit is the exact same concept as the control unit for a pushdown automata. It's the exact same concept as a DFA or an NFA. These things are really just finite state machines. They have states inside of them. They have transitions that take you from one state to another state. They have some kind of rule or rules that determine which moves or transitions from states are legal and which states are accepting, which states are not accepting, etc., etc. The second thing is a read-write tape. So previously for pushdown automata, we were talking about the stack and the input tape. The read-write tape in a Turing machine is effectively the combination of both of those things. So rather than having a separate stack to manage internal memory, what we have in a Turing machine is internal memory that also represents the input tape itself. So if you think of trying to solve a problem with a Turing machine, the read-write tape would begin with the string that you're trying to solve the membership problem for example. And then at the end of the computation, the tape could contain nothing, or it could contain something entirely different. The internal memory and the input of the problem both reside on that tape, and that's something that we're going to look at via example in just a moment. Then the third thing is the read-write head. So we talked very, very briefly at the end of the pushdown automata lecture about a thing called a stack automata that is capable of determining or understanding, recognizing context-sensitive languages, or a superset of context-free languages. And what we said about those automata is that they were a generalization of pushdown automata because we were able to treat the stack effectively like an array. So we're able to go up and down the stack. And we can do exactly the same with this read-write head. So we can go left or we can go right, unlike things like DFAs or NFAs, where you really focused on just progressing through the input left to right, never returning to a previous symbol in the input. So that's why this is kind of a generalization of all of those previous automata. So as with everything in life, Turing machines themselves have several rules. So if you were thinking about a Turing machine, if you just basically took a snapshot of a Turing machine, there are some specific things or pieces to the state of that machine that we would be interested in taking a look at. And so the first of those is the current state that the control unit is in. So it could be the initial state, it could be some intermittent state, it could be a final state. It's just whatever state that control unit happens to be in. The next thing we'd be interested in is the symbol that is currently pointed to by the read-write head. So this is very, very similar to the stack pointer in the push-down automata that effectively just sits at the top of the stack. Reading the current symbol, we would be interested in what the current symbol is, in addition to what state the control unit currently is at. In the last part, we would be interested in all of the information that is currently written to the read-write tape. So like we were saying before, the read-write tape can begin with the original input, but after some number of computational steps, that initial input could be in some intermediate state, or it could be in some final state that is drastically different from the input. And so all of these things put together, the current state of the control unit, the current symbol being pointed to by the read-write head, and the current state of the read-write tape, put together are called the configuration or the internal state of the machine. So if somebody gave you those three different pieces of information in your head, at least you would be able to draw a picture that looks extremely similar to this one and basically fill in the blanks. You would be able to say exactly what the state of the control unit was, where the read-write head was pointed, and the current symbols or the current string that's written on that tape. So if that is a snapshot in time, some time t of the machine, the computational rules are what allow us to go from state t to some configuration t+1. So when we're trying to update the configuration or update the internal state of the machine, we can do the following things. We can update the control state. So in that finite state machine that sort of implements the control unit, we can go to the next state depending on the control graph or the transition function. We can then replace the symbol that is currently pointed to by the read-write head. We can replace that thing with itself, that is, do nothing at all, or we can replace it with whatever tape symbol the transition function allows us to replace it with. And then we can update the position of the read-write head to go either left or right to update what the current symbol is for the next time step. And so basically all three of those pieces of information that represent the configuration or the internal state of the machine can be modified to come up with the next configuration or the next internal state of the Turing machine. So some notes about the tape. So the tape itself is bounded on the left but unbounded on the right. And so if you go back to my kind of Microsoft Paint diagram, you see here there is a boundary on the left, but there is not a boundary on the right. This causes quite a bit of sort of theoretical hand-wringing for a lot of people. But the thing to focus on is the fact that the tape being infinite is really a theoretical construct. What it means is that if you give me 20 million symbols as the input to a Turing machine, I am ensured that there exists a Turing machine that is capable of representing that input string. What that does not mean is that if you have a digital computer with a finite amount of RAM or a finite amount of disk space, that machine is not representative of a Turing machine. So what we need to do in our minds is kind of segment the theoretical and the practical aspects of having an infinite tape. Effectively, what's happening is a theoretically infinite tape allows us to do computationally powerful things. Practically speaking, we never have an infinite amount of RAM or an infinite amount of disk space. However, if we have enough disk space or enough RAM to represent the input that we're actually working on, then there is no difference, according to the Turing thesis, which we'll go over in the next lecture, between the digital machine that we're actually using to represent the Turing machine and the theoretical construct of a Turing machine. So there's a lot of questions, if you were to go to something like Quora, on if digital machines are actually representative of Turing machines, given the fact that they have a finite amount of space. The answer to that question is yes, they are, because as long as you can represent the input that you're trying to compute, the size of the tape is sort of inconsequential to the computation itself. So the next thing to think about is the fact that the tape has a completely different alphabet than the alphabet of the original input. And so this was also true for push-down automata. We can have some alphabet, we called it gamma then, that contains characters that are not in the original input alphabet. So for example, we can use special characters to cross out characters after we've processed them on the tape, for example. This is something that we're going to do in the example in this lecture. Speaking of, there is a special symbol usually denoted by this kind of cup, sort of square U kind of thing, that denotes a space on the tape. In almost any text that you look at, or any sort of set of sort of assumptions about Turing machines that you might read, all of these things consider this cup or the space to be a special symbol that is in the tape alphabet, but not necessarily in the input alphabet. And so even if the input contains something like a space, so if you're trying to process whole strings or something like that, there would be a special space that is usually used to denote the end of the input, the end of the input value. So this is something similar to the end of file character or something like that. And basically what we do is we use that to make the infinite tape finite in terms of computation. And so we've talked about this several times, that what we're really interested in is computing finite strings in potentially infinite languages. So this is one way that we can use to kind of denote the end of the input as we know it. So the example that we want to kind of motivate this entire idea with is a language that consists of any series of zeros and ones suffixed with a pound sign or a hash sign, and then that same combination of zeros and ones appended to the end of it. And so you can fairly easily convince yourself that this is not a regular language. You can also kind of convince yourself that you might have some difficulty trying to derive a context-free grammar for this particular language. However, what we're going to do is we're going to show that Turing machines can actually identify whether or not a specific string is in this language. And so one of the things that is going to come up over and over and over again as we kind of study Turing machines is the idea that algorithms themselves start becoming much more familiar when you're talking about something like a Turing machine. So previously, we were able to think algorithmically, but if you tried to write down what the algorithmic steps were, they tended to be extremely low-level steps. So those were individual transitions inside of DFA, for example. And so this is something akin to programming in something like assembly language, for example. For Turing machines, however, trying to develop algorithms is much closer to something like C or C++. So what we're going to do first is we're going to try to think of an algorithm that will allow us to understand if a string is in the language you just discussed or not, using only those rules that we discussed a couple of slides ago. So we can think about the internal state of the control unit. We can look at the current symbol at the read-write head, or we can move that read-write head right or left. So the first thing that we know is that the read-write arm is probably going to start on the leftmost edge of the tape, and if it doesn't, we can make it. So let's just assume that the read-write arm starts at the leftmost character in the string and right next to the sort of edge of the tape on the left-hand side. So if we read that very first character, what we can do is we can move the state in the control unit to a state that remembers what that symbol was. So if you remember all of the DFAs that we've created, all of the NFAs that we've created, even the ones on the midterm, for example, to determine if you see a substring of 0, 0. You can remember what that first symbol was by moving either to a state that is marked as 0 or a state that is marked as a 1. Next, what we can do is we can stay in that state and move right until the symbol that we were pointed to with the read-write head hits that hash symbol that we know marks the sort of midpoint in all of our strings. Once we hit that midpoint, we'll then want to read whatever character is to the right of the midpoint and move to a representative state. So if we read a 0 to begin with, and then we read a 1, we would want to move to a state 0, 1, or a state 1, 0, or 0, 0, or 1, 1, depending on what the two characters are. That is, the leftmost character of the first W, or the leftmost character of the W after the hash symbol. So if we arrive in either 0, 0 or 1, 1, we know that everything's cool. We've matched on the left hand and the right hand side of the hash symbol, and so we can move on to the second symbol in each of the W's, match that one, move on to the third string, move on, third symbol, move on to the fourth symbol, so on and so forth. The problem is trying to get through all of the kind of details around how to get back and forth and kind of zigzag between the symbols inside of both of these respective strings. So what we're going to do is kind of look at this as a kind of animation to kind of illustrate what the algorithm was that we were just talking about. So if we start on the leftmost part of the read-write tape, we see that that thing is a 1, and then we move all the way to the midpoint. We see that this thing is the hash, which indicates the midpoint of the string. We can go to the right of that one. We read another 1. We update the internal state of this control unit to the state 1, 1. And because 1, 1, we know that we are on the right path. If we were at a 1, 0 or a 0, 1, we would know that we could immediately kind of reject the string. We know that it is not, in fact, an element of the language that we're trying to compute. The problem is we can't just go back to the beginning of the tape. So if we look back at what we were doing, we don't necessarily have any internal states inside of the control unit that will tell us when to stop going back. So here we would have to effectively count only 4 moves, as if we went all the way back to the beginning, we would just be stuck matching this one to this one over and over and over again. So we need some mechanism for telling the machine that we should actually stop at this 0 and not go back to the original 1. So how can we do that? What we need is to be able to mark each of these characters that we've actually already matched so that we don't process the same character twice. So what that's going to look like is, instead of just leaving the 1 on the tape and then progressing to the hash sign, we're actually going to replace that 1 with an X, meaning that we've already seen it and we've processed it and we don't need to care about it anymore. So now we've read that 1, we're going to update the internal state of the control unit. We're going to replace the 1 with an X on the tape. We're going to proceed to the hash sign. We're going to look to the right, recognize that this thing is also a 1, replace that 1 with an X, and now we can go all the way back to the left until we see an X, move 1 space to the right, recognize that this thing is a 0, replace that 0 with an X, then move to the corresponding character after the X to the right of the hash sign, and then zigzag back and forth and back and forth and back and forth. And ultimately, for this string, what we're going to see is that we have a whole bunch of X's, a hash sign, and then another whole bunch of X's. In the event that we have no additional input on the tape, that means that we have finished in a final state and all is well. We have answered the membership question, and it turns out that this algorithm will work for any arbitrary string inside of that language. We have a Turing machine that will tell us that yes, indeed, this string is inside of the language. So this brings us to the idea of accepting and rejecting, which is sort of like push-down automata, slightly more nuanced than it was inside of something like a DFA or an NFA. So if you recall, for PDAs, we didn't actually really care what was left on the stack once we landed in a state after processing all of the input. The only thing that we cared about is if we ended up in a state that was accepting or not after we ran out of input. The same is true for Turing machines, except Turing machines typically also have kind of special behavior for accepting and rejecting. It turns out that these assumptions that we're talking about right here don't necessarily affect the power of Turing machines. They basically just make things easier to algorithmically represent on Turing machines. And so we can basically assume that all Turing machines that we're going to be talking about have 2 special states. One that is an accepting state, where if you end a computation in that state, the computation is accepted or the string is accepted. It is, in fact, an element of the language that we're interested in. Or the reject state, which is kind of like a trap state, in that once you hit that reject state, computation stops and the string is completely rejected. So the nuance here is that unlike push-out automata, unlike deterministic and non-deterministic finite acceptors, we have accept states and reject states that once we hit them, computation stops. We don't necessarily have to finish computing or looking at all the input. Once we hit these states, computation is over, and we know either the string is accepted or the string is rejected. So if we kind of apply that ideology or that idea to the previous example, we can come up with some rules that allow us to determine when we can move to an accepting or a rejecting state based on the input that we have left on the tape. So if we go back to our example here, we know that if we move to the right, what we're going to find is we're going to find a space symbol. We're actually completely out of input. In that case, we know that we can accept if and only if all of the characters to the left of the pound sign have already been processed. That's basically taking into account the case where we have an equal number of characters to the left and to the right of the pound sign, and by computation we know that all of the symbols are the same. So that's the case in which the string does in fact belong to our language. So if you see anything other than the space after you have processed all of the characters to the left of the pound sign, we would want to move to a rejecting state, because that would be the case where the W to the right of the pound sign is actually longer than the W to the left of the pound sign, which means that the two W's can't possibly be equivalent. Also, if you ever find yourself moving into a state 0, 1 or 1, 0, you can actually move from either of those states to a rejecting state, because what you've done is you found a pair of characters at position I in either of those strings W that are mismatched. So if you find a mismatched pair, that means that the W's cannot possibly be equivalent on either side of the pound sign, and you shouldn't have to compute anything else. If you found one mismatched pair, then you know that the W's can't be equivalent, and so you should be rejecting the string. So we have made a lot of fuss previously to define what we've called L of M, and basically we've always called that something like a language that has been accepted or a language that has been generated by some sort of construct, be it an automata or a grammar or a regular expression or whatever, that we called M. So if you remember back for regular expressions, we said if we have some regular expression R, we have L of R as being the language that is represented by the regular expression R. For Turing machines, that's where this kind of concept really becomes very, very important. And the devil here is really in the details. So there are many different sort of terms for what it means to be accepted or generated by a Turing machine, and that's what we're going to talk about for the remainder of this lecture. So the first piece of terminology is called recognized or recognizable. So a language is said to be recognized by a Turing machine if for any string inside of that language, we have a Turing machine M such that that machine stops at an accepting state if the string is in L, but if the string is not in L, it either stops in a rejecting state or it stalls in a not rejecting and not accepting state, or the computation never ends. So basically, these kinds of machines can tell you with certainty that a string is inside of a language, but they cannot necessarily tell you that a string is not in a language. They could just compute for forever and ever and ever, and you wouldn't necessarily know if it was not returning because it's just taking a very long time to determine membership, or if it's stuck in an infinite loop and will actually never terminate. On the flip side of that, a language is said to be decided by a Turing machine if the Turing machine can actually tell you not only if the string is in the language L, but also if it is not in the language L. So a Turing machine that decides a language, or a language that is decided by a Turing machine, will stop in a reject state if the string is not in the language, or it will stop in an accepting state if the string is in the language. So the key difference between recognized and decided languages is that decided languages always give you a result. If a language is decidable, that means you know that a specific string is either in or not in the language. If a language is recognized by a Turing machine, you know if the string is in the language, but you don't necessarily know that you're going to get positive verification that it is not in the language. So a Turing machine that recognizes a language is said to be a recognizer for that language. And so this basically just flips the terminology. So if I have a recognizer, that means I have a Turing machine that can tell me if a string is inside of a language, but if the string is not in the language, it might enter into an infinite computation and not actually tell me a result. A Turing machine that decides a language is a decider for that language. And so a decider is capable of giving me a positive, yes, this string is inside of the language, or telling me, no, this string is not inside of the language without entering into an infinite computation. So it is true that deciders are always recognizers, but not all recognizers are deciders. And so this is kind of obvious because a recognizer could potentially halt or stop inside of a rejecting state for a string in a language, but we also have some recognizers that enter an infinite loop for strings that are not in the language, and those recognizers would clearly not be a decider for that language. So if you were to choose either a recognizer or a decider, you would probably much prefer a decider because deciders can actually definitively answer the membership question. Given only a recognizer, if you do not know if the string is in or not in the language, and the string ends up not being in the language, you could potentially just wait for an infinite amount of time and make the determination based on the amount of time you're waiting that the string is not in the language. However, for a 2 bajillion character string, it could just be that the membership question takes a very long time to compute, and it is in fact in the language. So recognizers are very difficult to practically use. If you've ever tried to do some sort of like very long computation, maybe training a neural network or something like that, it becomes kind of a practical question. After 4 days of training, do you have a cost function that will ultimately converge one day, or are you kind of stuck in a situation where the computation will go on for forever? In a very real sense, theoretically, that's what a recognizer gives you. A decider, on the other hand, will always terminate and will always tell you if a string is inside of a language or not. So to finish up, if you think all the way back to the second lecture in the class, we talked about how in the wide world of theoretical machines, there are really 2 different types of machines. There are acceptors, which we have been dealing with exclusively up to this point. Acceptors largely deal with language membership, and really what acceptors can give you is a Boolean value. You give an acceptor an input, and the acceptor tells you yes or no, and typically that yes or no question is this string input that I've given to you a member of the language that the machine is set up to recognize. Transducers, on the other hand, can actually produce what I've put in giant sort of quotes, meaningful output, which means that transducers don't necessarily provide only a Boolean result. What they actually provide can be much, much, much more robust. So transducers are much closer to our concept of what a digital computer actually does. It can take some input, and it can transform that input into an arbitrarily complicated output that is stored on that read-write tape that we've been talking about for Turing machines. And so it turns out that Turing machines can actually be either an acceptor or a transducer. And so there are techniques to take each of the acceptors that we've talked about in the course and try to make them into transducers. There are generalizations, but Turing machines are really the first time in the class that we've had a meaningful way of actually doing transducer logic. So where we want to stop is a concept called Turing-computability. And so we've talked about the difference between acceptors and transducers, and the fact that Turing machines are capable of being transducers is really a kind of precursor to the idea that Turing machines can actually take an input written on the string and then implement any sort of arbitrary function that you can imagine. So, for example, we could have a function that simply copies whatever input is on the tape to the end of the tape. This is possible because that problem is Turing computable. What Turing computable means is that if I have a function, not necessarily a mathematical function, but any function that has a domain in which we have elements, and it has a range in which we can map those domain elements to, there exists a Turing machine that can take that initial input and can stop in an accepting state that results in the range element being represented on the read-write tape. So effectively what this means is I have a Turing machine that for that function goes through all of these intermediate steps to transform the input or some element of the domain into some element of the range of that function before reaching an accepting state in the control unit. And so it turns out that all of the sort of common mathematical functions that you can think of, regardless of their complexity, regardless of the number of times they're nested in each other, regardless of if the numbers in the domain are transcendentals, that they have an infinite number of decimal places, all of that is kind of not relevant. All of these things are actually Turing computable. And so this is kind of the first step on the path that takes us toward what's called the Turing thesis, which we'll talk about in the next lecture, which effectively says that Turing machines themselves provide the theoretical underpinning for digital computers as we know it to actually mechanically make a lot of the computations and represent a lot of the functions that we use sort of every day. So that's really it for this lecture. What we're going to do next time is we're going to look at examples of much more complicated Turing machines. And so what we're going to do is start off with the kind of mathematical representation of a Turing machine. What is the definition of a Turing machine? And we're going to go from that definition to an example that actually shows that Turing machines themselves are capable of arithmetic by showing you how to do multiplication on the read-write tape. Then what we're going to do is look at combining Turing machines to tackle complex problems. So by complicated problems, I mean problems that require multiple steps or multiple algorithms to get through. We're going to show that effectively we can just string Turing machines together, largely like we did with schemas for showing things are regular languages, like the complex numbers question that we had for the homework. Then we're going to introduce the Turing thesis, which, like I said before, is basically the thesis that tells us that the Turing machine concept allows us to theoretically represent all of the different computations or all of the functions that an actual digital computer can perform. And so this kind of theory gives us an idea of the power of our own digital computers and all of the different problems that they can actually solve. And so this thesis is going to prime the sort of back third of the course, which is really about computability, the complexity of computability, and P versus NP and that kind of thing. So that's going to wrap up this lecture. I'll be posting the next one shortly, maybe tomorrow. And so through this week, we'll be getting through chapter 9 of the textbook. We're going to try to keep to about a chapter a week, so that we cover the entire textbook. In the event that you're sort of going on to the graduate course, you'll be very well prepared for that. So thank you for tuning in, and I will talk to you next time.